on activity planning draw upon the work in the formal methods community whose expertise is in verifying current systems.
Thanks, Brian. It's a pleasure to be here. Many thanks, Brian, for the invitation, and many thanks to all of you for being here despite it's been a long day already. Given that this is the last tutorial, I'll be only partly technical. I'll also be non-technical, trying to be, I guess, motivating and inspiring, hopefully, mainly on the point that I guess that planning can play really a key role nowadays that everyone is talking about AI and robotics. That's the reason why I put that subtitle there. I mean, I'll tell you more why I choose that subtitle. I will start with the video, a small video that I took with my iPhone 1 year ago, more or less, when I was in Pittsburgh. I had to take a Uber from the hotel to the conference venue, and the app offered the opportunity to have a self-driving Uber. So I said, yes, of course I want to try it. I couldn't wait. And I took this video with my iPhone. So it was raining. So this is the driver that starts the vehicle and then stops driving, but it stays there just to check if everything goes, if anything goes wrong. And again, it was raining, so the system was reacting quite well, also on bad weather condition. They are explaining, because I was asking questions, but what is very interesting to me is that now there is a second Uber human operator, which is checking with his laptop whether the sensor, the perception, is actually correct. So the story here is that now, thanks to AI, in order to drive a vehicle, you need 2 people rather than 1, right? So AI is creating jobs, you know. But the point I want to make here is that, as a matter of fact, everyone, of course, AI is becoming really ubiquitous, right? So it's everywhere. And there is a lot of research and a huge progress in AI. However, no matter what, there are still serious concerns about the safety and trustworthiness of AI. Because, you know, in critical systems, you cannot guarantee many times the behavior of your AI system. That's why you need 2 people for checking the AI is doing right. And my, let's say, selling point here is that there are many people who do AI, but there are not so many people who do safe and trusted AI, meaning people that are trained and do research on safe and trusted AI. And perhaps some of you will do, even, you know, inspired by this talk, I hope. So why I'm talking about these things and why I've been focusing my research on these things over the last 2 years, one reason is that at KCL, King's College London, where I come from, they created this Trusted Autonomous Systems Hub, and I was asked to lead this hub. And the idea is to focus on many AI techniques that can help in creating trusted autonomous systems. And when we talk about trust in autonomous systems, we refer to something that is related to the whole life cycle of the AI system. So it's not just that you create AI and then you verify the AI, but from the beginning, when you design AI, you want to be careful about the safety and the trustworthiness. And so that's why, for example, you use planning or formal verification while executing and also while validating the system. So through all the life cycle, you should care about safety and trustworthiness. So in this lecture, I'll try to do 3 things. First, to talk about planning as model checking. Then SMT, which is something that borns from model checking, how to use it for planning. And then talk the last bit about explainable planning, because there has been a lot of interesting work around explainable planning over the last year. So I want to give you an overview of where we are. So planning as model checking. This is a paradigm that was originating a while ago in '97. And there are a number of papers around the same year from this bunch of authors, basically. This is one of them, perhaps the most representative, and this was published in ECP 97. Does anyone know what ECP is? Which conference is that? Right, so it's European Conference on Planning. I think it's the grandmother of ICAPS, probably, right? And again, mainly Paolo Traverso, Giunchiglia, and Alessandro Cimatti were the fathers of this paradigm called planning as model checking. And I will use 2 slides to introduce the concept. These slides are taken from AIPS 2002. Do you know what AIPS conference was? So a bit of history, right, of our community. So that was, it's international conference on AI planning and scheduling. So this is the mother of ICAPS, right? So from European, then we move to this. And actually I also found a couple of pictures with some of us there. So you should recognize this guy here and also this guy here that was here yesterday. So I wasn't there yet, so anyway. What is planning as model checking? So model checking is a technique that is used to validate a formal model, so to verify the behavior of a formal model. And what you have is that you have a model, some formula, for example, a safety property, and then you have this model checker that either tells you that, yes, the system verifies the formula, so it's safe, or if not, gives you a counterexample, which is a trace from the initial situation to the situation that violates the safety property. Now, you can see how sounds very relevant to planning, right? Because also in planning, you want to find a sort of plan which is similar to the error trace. And in fact, in planning, basically you have, let's say, really the analogy between model checking and planning, where instead of the error trace, you find a plan. So based on this simple idea, there has been a lot of work on how to use all the techniques developed in model checking, particularly in reachability analysis, how to exploit those things for planning and for finding plans. Recently, this is 2014, a Dagstuhl seminar was organized. So Dagstuhl is a location when you gather together with a bunch of people for 1 week. Given that it's in the middle of nowhere, you can only, focus on research around a specific topic. And again, some people were there. So it was a nice week. Just to highlight the fact that this topic around planning and model checking is still active. Now, myself with my team have been focusing on using this paradigm for planning for hybrid systems. Now, you already heard a lot about hybrid systems in these days. I'll give you an example of how planning as model checking can be used on this kind of systems. And this is the technical bit for today. So PDDL plus, just a note, if you have any questions or comments, please feel free to interrupt me. Now, PDDL plus is the extension of PDDL for handling hybrid systems. Before we talked about timed automata, in hybrid system we use hybrid automata, right? So we have discrete modes, and in each discrete mode there is a continuous evolution, okay? So you jump between these modes using discrete actions, and in each mode then you have a continuous evolution of your state variables. In PDDL plus we have processes that model the continuous change in the environment. So if I open a tab, there is a water flowing, that's a process. And events that models what happen in the world. So they are not action from the planner, but events, exogenous events that happen. Now, one way to approach hybrid systems, where the continuous dynamics is an issue, of course, is challenging, is to use what is called the discretized and validate approach. The idea here is that we start with a continuous model, with the continuous differential equations. We discretize the continuous model. We'll see in a bit how we discretize. And then we solve the discretized model. And this is where the model checking technique is used to do the reachability analysis in this discretized setting. And then we validate the solution we found against the continuous model to check that the solution we found with the discretized model is still valid according to the continuous model. If it's not valid, then we iterate, we refine the discretization and we iterate. Of course, finding a good discretization is not easy, because if you use a too-coarse discretization, you risk to miss information. And if you use a too finer discretization, the problem is that the finer the discretization, the bigger is the state space. That's why you need to use an iterative approach. Just to give you an idea, of course, discretization involves discretizing variables. So depending on the discretization you use, your state space really explodes. And discretization involves discretizing time. So the important point here is that the time in your model is continuous. But the way you solve your problem is by discretizing time. But originally, your model has got a continuous timeline. Right, so the clock ticks there is the way we discretized the timeline in uniform time steps. But again, even time discretization is an issue, because if you refine too much the time discretization, you end up in a, the choices you make really make the state space too big. Now, a benchmark problem in the planning community, in the habit system planning community, is the so-called generator, which is very, simple as the idea, but presents a number of features which are interesting for a number of real scenarios. So the idea here is that the generator must run for 100 seconds or 100 time of units, and it consumes fuel for running, of course, and there is not enough fuel in the generator for completing the action, so you can use some tanks to refuel the generator while you are using it. As simple as that. The problem is that the planner has to decide when to refuel in order to avoid that the generator runs out of fuel, or that you put too much fuel in the generator, right? Because there is a fixed capacity. I'm using this example just to show one thing. So that's a possible plan for the generator. So you start generating fuel, and then you use at these time points the two tanks that you have available. And this is the continuous behavior that you observe in the level of fuel in the generator and in the two tanks. Now, these reports, I'm showing this for this reason, are created by VAL. I don't know how many of you are familiar with VAL, but I guess VAL is a very important tool in the planning community. VAL stands for validator, right? It's an open source tool that allows you to take an input, a planning problem, a planning domain, and a plan, and validate it. So to check whether it's valid or not. That's important because there are, of course, problems where it's very simple to check that your plan is valid. But there are a number of problems, particularly when you have complex dynamics, where it's not obvious at all to say, okay, that's a valid plan or not. VAL allows you to check these, and as we'll see in a bit, also allows you to detect where there are problems, okay, and why, for example, a plan is not valid. Now, a second example I want to give, it's this one, which is relatively old. I think it was 2011, no, it's 2013. However, we recently started again working on this because a few companies got interested in this work. So the idea here, and this was done by me in collaboration with Marie and Derek, the idea here is to use planning for, let's say, scheduling the behavior of multiple batteries. So every time you have more than one battery, as this is the case, for example, for electric vehicle, as well as in the military domain as well. So you have many scenarios where you have more than one battery. The way you decide to use the batteries can result in a much longer lifetime. What you don't have to do is just to use battery 1 first, and then battery 2, and then battery 3. Why? Because you can never use all the charge in the battery. Instead, before the battery dies, if you leave the battery some time to rest, it somehow gains some charge for the nonlinear behavior of the battery. So if you start using a battery, then you switch to another one, giving rest to the first one recovers while using the second one, okay? And then you can swap again. There is a lot of research going on, and we try to use planning, and we show that we really improve the lifetime of multiple battery system using planning. That's just to give you a flavor of a PDDL plus model. Now, not many of you knew PDDL, I guess even less you know PDDL plus. But just to give you the intuition, so this is the nonlinear dynamics. And again, the message here is that PDDL is not just to model Bloch's world, with all my respect to Bloch's world. You can also model many, many complicated things, including differential equations and complex dynamics. This derivative action is used to decide which battery to use. You can have n batteries, right? So with this action, the planner can decide which one to use. And these processes here are used basically, it's the PDDL plus representation of these dynamics here, okay? again, if you think about the hybrid automata I showed before, the discrete modes are which battery to have on or off, and for each discrete mode you have a continuous change that, you know, tells you how the charge in each battery goes up and down. And once you have this domain, the way you describe the problem is, this is one example. So here you have the parameters of the batteries, the chemical property of the batteries, and this is interesting because this is the set of time initial literals, which are used in this case to model which is the load that you have to service with your battery. So here we are saying at time 0 there is this load, 0.5, then at time 1, 0, and then, you know, we have this kind of load that we want to service. Again, time initial literals are a way to describe in your initial state something that will happen in the future. Usually the demand is modeled using time initial literals. Okay, is this clear so far? Okay. Again, the way, okay, of course the goal is just to complete the load profile without violating the main property, and the main property is that there must be always a battery on when there is the load to service. Now, again, we use the planner UPMurphi. That's old, was done in my PhD thesis actually, but the idea of this planner is basically to use, so the reason why it's called UPMurphi is because Murphy is a popular model checker. So it was used to do model checking in the past using a forward search reachability analysis without any heuristic. Because something I didn't mention before, in model checking, you need to check all the states because you want to verify that all the states satisfy your safety property. So while in planning you can prune the state space and go directly to the goal, in model checking you need to check all the states. There are different ways to do that. Murphy was a model checker that used a reachability analysis without heuristics. So UPMurphy doesn't have any heuristics, so it's blind search. And of course the actions are which battery to use, and the goal is to maximize the lifetime. It's based on discretization, as I said, and that's an example of how discretization works. So we started using a discretization of 0.1 second, and this is the plan that was found. That's an example when you only have 2 batteries. Then we tried to validate this problem, this plan, and that was the response from Val, which is saying that the plan is not valid because of this. Now, can you spot why the planner found this plan which is not valid? Do you, or in other words, do you find it surprising that the planner finds a plan which is not valid based on the setting we use and in the response from Val? Because of the time, you are right. So the time we are using here is 0.1. And in fact, you see interaction only to this time scale. What Val finds that there is a change in the battery at this time point, 5.08, which is, you know, too fine-grained for the time discretization that we are using. Okay? Means that what happens is the following. The charge in B1 becomes 0 at this time point, so slightly before we switch to B2. Okay? So that the planner couldn't notice that. So what we do is that we refine the discretization to 0.01 now, and this is the new plan where, as you can see, there is a switching straight just before the battery dies. That's a small example on how you can play with the discretization, first. Second comment is that, of course, planning allows you to create correct back obstruction solution modulo the fact that your model is correct. Okay, in this case, one issue here is the discretization we use. Just to give you an idea of results, because in planning we always have to show graphs apparently, so here there is one, and that's the comparison between what the planner finds and the state of the art, which is basically round-robin scheduling between the batteries. What is interesting is that there is no clear pattern here, so nothing that you could learn from, for example. It's really a strange behavior that the planner found. The nice point of using model checking, at least in my opinion, is that the model checking community did a lot of work in creating efficient algorithm and efficient data structures. So in some sense, we can leverage the effort that has been made in model checking. And as I said, UPMurphi performs a blind search, which is not good in general, right? However, it's quite easy to introduce in UPMurphi domain-specific heuristics, so that then you can use in practice for real application, you can use UPMurphi quite successfully, as in this set of things. There has been a development on UPMurphi, so first we try to introduce domain-independent temporal relaxed planning graph. So what you have basically, the RPG version, temporal version of RPG embedded into UPMurphi. This was barely the thesis of Victor Petrosky. And then we also extended with using pattern databases, has been rejected a number of times. So the message here is never give up if your papers get rejected, but keep trying and fighting for the work that you find is worthwhile. Now, open challenges in this setting, in discretization-based model checking applied to planning, is that so far we have been using a uniform time discretization, meaning that you have discretization of 1 second every time you discretize the same thing. But there are many scenarios where there are part of the state space of part of the plan when you can really, make longer jumps. You don't need to check every seconds. And part of the state space when you need to be very careful. So the idea of using a variable or dynamic discretization is what we are now investigating. Mixed approach, so you could use linear for example, linear programming when the dynamics is linear, and then move into this discretization when the dynamics gets complicated. Do you have a question?
Yeah.
Please.
I have a question from a couple of slides where we went through the example. So I was just curious, the error that we had was about 0.02 a second. It was the difference in the...
Oh, the previous one then.
Yeah. That's okay. Yeah. So the difference is about 0.02 seconds. Depending on the problem domain, it becomes relevant if that 0.02 seconds is really important for the problem. It depends on what is this solution relevant for, what this application is relevant for.
So I'm not sure about the question.
Yeah.
For sure, the discretization depends on the specific problem you want to solve.
So one of the interesting themes from today morning was whenever you want to go deeper and deeper, it is also interesting to get a bit more abstract. So instead of trying to iteratively check what is the discrete time interval that is necessary, do you think it is also interesting to think about how would you frame a formula that is much more abstract and checking for time discretization or something that is much more final than just looking at something that would be much more abstract?
What do you mean when you say abstract? What are you thinking of when you say abstract?
So I'm thinking of, is it within a range? Is it within a range of the necessary time interval? Say in this case, the discretization always happening at 0.1 second. I want to encode a much more abstract way saying that, okay, it could be 0.05 seconds.
I guess it's a good idea. We should talk definitely offline. At the moment, there is no clear guidance, not even in the model checking community, on how to find a good discretization.
Oh yeah, the
Right.
only reason I'm asking that question is because were there any work that was done which basically looks at looking at abstract formulas? For
Yeah. This is also an open challenge in planning, but definitely worthwhile to follow up, right? What is key is that you can validate anyway the solution, right? It's not that you trust and you just guess. You start with something and you validate and you get inside and you improve. Thanks for the question. I forgot to mention that, the good point of this approach is that you have no limitation in the kind of non-linear dynamics that you can handle, right? Which is a good step when you have complex systems. What we are looking now is how to introduce landmarks in order to help this kind of approach to scale. Now, the second branch of model checking techniques that can be used for planning is the one based on SMT. How many of you knows what SMT is? SAT modulo theory. Okay. Okay, so let's start from one step before. Raise your hand if you know what SAT is. Satisfiability. Okay, better. Okay, for those of you who don't, we are in a school, so we need to learn, right? That's the problem in SAT. Given a set of Boolean variables, right, in a set of clauses, find an assignment to the Boolean variables such that the formula is satisfied. For example, if you have this formula, is this set of clauses satisfiable? Meaning, can you see an assignment to the variable so that the formula is satisfiable? I won't go ahead until you answer, so better for you to answer, otherwise we stay here until night. And then the following question is, why, right? Otherwise 50% chance is too easy. The answer is yes, you're right, but why? Or, in other words, can you give me one possible assignment that satisfies this formula? There is not just one, there might be many, right? Ben, say again? Y true is Z true? So, Y, yes, correct, fine. And now if I add something here, is still satisfiable? I guess we didn't change too much compared to what you suggested. But what about this then? Your solution is no longer valid, right, Ben? And I mean, you can quite easily check that there are no feasible, no assignments that make this formula true. Now, you can think that there are many important scenarios where you have formula with a lot of variables and a lot of clauses. So solving this problem is not easy at all. It's an important problem. Now, SMT is let's say, an evolution, if we can say this, of SAT, where the idea is that now, instead of having a Boolean formula, I have a first-order formula expressed as in a theory, and I want to check whether there is an assignment for that formula. So, for example, again, if I have this formula now, is this satisfiable? Yes? Raise your hand if you think it's satisfiable. Raise your hand if you think it's not satisfiable. Okay, there are many who just don't care, so the difference, right? Who is left? Okay. Any more ideas? Any more thoughts? Okay, you seem to converge on the fact that perhaps it's satisfiable. Some say satisfiable, some say it's not satisfiable. You are all wrong, unfortunately, right? Because the real answer is, it depends. Why? I didn't give you the domain. Bravo, that's good. I didn't give the domain of X, right? Without the domain, we cannot say it's satisfiable or not, right? And in fact, is it satisfiable in the theory of rational arithmetic? Can you give me a value for X? Right, but then instead if I ask, but what about the integer arithmetic, right? There is no solution. So SMT is this kind of problems where we no longer have only Booleans, we have theory. And theory can involve many things. What is good about SMT is that there is a strong community on SMT. Many theory are supported. You can deal with many different kind of objects. Many solvers, SMT solvers, and there is also a solver competitions since 2003. Many thanks to Andrea Micheli. He did a nice, very nice PhD thesis on SMT for planning, so you can look up after what he has been doing. That's just a list of examples of possible different theories you can use in SMT. So again, it's kind of pushing the kind of the expressive power and the set of domains you can deal with. And that's a list of solvers. Just to give you an overview. And SMT is used in many applications, again, mainly and originally in model checking and formal verification, but then in a number of domains, including planning. In the planning community, there are many people doing planning through SAT first and then SMT. I don't have an exhaustive list. I suggest you go and look for the work by Jussi Rintanen on planning accessibility. This is a nice overview. You can go and read it. What I want to talk to you about in the next few minutes is, again, how SMT can now be used for planning for hybrid systems. This is the credits here basically go to Michael Cashmore and Parisa Zetabi. The idea of SMT for planning is that you basically encode in a SMT formula what should be your plan, potentially. And then you ask the SMT solver to find an assignment to variables so that your plan is valid. Okay? So think about what we showed before with the variable x. Now you have a plan with some variables, and one of the main variables is time, meaning when things have to happen. And you ask the SMT solver to check and to find an assignment to these variables, including the time variables, so that the plan is valid. That's the secret behind planning through SMT. And in particular, the idea here is to use happenings. So happenings are these verticals, which happen in specific time points that are found by the SMT solver. And in each happening, you have a chain of possible discrete events, discrete things that can happen. While between happenings, this arrow here represents the continuous change, meaning I do something, and before I do something else, there is a continuous change in between. The SMT solver will decide when to put these happenings in time. Again, the timeline here is continuous. Now, one problem with continuous change is what is called zero crossing problem. So every time you have invariant, also David mentioned invariant before. Now, if you have a linear dynamics, if you have an invariant between two intervals, you can just check the stream and check if, you know, the dynamics crossed your invariant and violated your invariant. If it's nonlinear dynamics, that's no longer true, as it was the case in the battery, because in the battery problem I showed before. Because it might be the case that in the interval, you are satisfying the safety property, suppose this to be greater than this value, but in between, you violated them. So if you only check at the extreme, you are not checking the important part, which is where the property is violated. Okay, in the encoding, that very briefly here, just to show you the fact that all the components of a planning domain and then of the planning plan can be easily encoded in SMT. And what you do is basically that in each happening, you have a chain of possible, for example, events that are triggered, or proposition and function, meaning which values your variables have, and which processes are active, and also which action you perform. So in each happening, you put all the possible things that can be present in the plan, and leave the SMT to figure out how to find a good assignment so that the plan is valid. So it's a very powerful tool that you can use, the SMT machinery. The problem was to come up with a valid encoding. Epsilon separation, that's too technical, but the idea is that in the semantics of PDDL+, if something happens, you can only access that resources epsilon time afterwards. Why this? Because it's to avoid that for a planning to be valid, you cannot require one action to happen exactly in these time points, right? So you give kind of tolerance, which is called the epsilon separation. So as I said, you encode the whole plan, and then you leave the SMT to figure it out how to do it. Just a couple of slides, very technical, on the maths. How do we handle the maths? Because we said you can start with the domain where you have complex differential equations. So what we do is that we use the computer algebra system, and the idea is that before encoding the plan, we consider the dynamics of the system, and we compute the indefinite integrals to be put in the plan. So making things a bit easier, perhaps, if we have this process here, just increasing the velocity depending on the acceleration, the CAS, the computer algebra system, what it does is to find this indefinite integral so that, let me skip one thing, so that, sorry, it becomes this integral, indefinite integral between happenings, so that you know which kind of dynamics you need to compute between each happenings in this time where there is only continuous change. And this is what the SMT solver will do for you. Well, we then did some experiments and we found that it scales very well in the continuous part of the problem. When you have a significant discrete combinatorics, things are not easy for SMT. It struggles. So if you have any idea on how to fight the discrete state explosion, come to talk to me and let's work on this. Because in the paper we say it's great in continuous change, but it's not so great in the discrete change. So it means that there is still something to be done. Okay, and SMT plan again, you can download it, it's open source. It cannot handle all the nonlinear dynamics. It can handle the nonlinear polynomial dynamics, which is still a lot, by the way. And the reason for this limitation is still the zero crossing problem. Okay, so if you have more complex dynamics, you are not sure that you can spot and check that safety properties are satisfied. Assuming you have the nonlinear polynomial, again, your plans are correct by construction. So that's a guarantee about the behavior of your plans. Open challenges here. So as I said, the nonlinear polynomial change, it's a limitation currently. It's not so powerful for the discrete explosion, and there is no heuristics at the moment. So basically, we encode the plan, and then we ask the SMT planner to solve the problem without giving the SMT solver any help from the planning domain. The next step will be, well, the next research question we are interested in is, given the domain, is there any information we can give the SMT solver to help the solver to come up with a solution more easily or more quickly? Landmark happenings means, is there any way to put some, again, because at the moment we give the plan to the SMT solver with no guidance on how to put the time points, the happenings. Is there any way to fix some of them and leave the others to the solver to find? And finally, combine SMT with control parameters, which is actually almost done. We'll talk next year maybe. Okay. Do you have a question? In this sense, well, it's the fact that you don't want to have action when you say x is equal 5, but you want to have a range, right? So to allow the planner to make a choice. Okay? Before I move into the next topic, which is explainable planning, any question on this so far? Okay, I will put on the Dropbox folder all the references about bunch of literature on SMT and SMT for planning. Now, explainable planning. Okay, that's very dear to me as a research topic, but also because I think it's a one way to highlight why planning is an important part of AI, okay? Which is something we should fight for because it's not so obvious for many people. The motivation for me to work on this over the last year or so, first of all, comes from money, in the sense that there are some funded projects that require this. So, we do research, we need money for our team. And the projects are the following. So this is the JET, Joint European Torus. It's basically part of a nuclear reactor in somewhere in UK. And they want to use this kind of robots here for the maintenance of this environment. Now, no need to say that it's a dangerous environment. That's why they want to put robots in this space. But it's a high-risk missions and critical safety constraints. So the point is there before accepting a plan for this robot, they want to make sure that they understand what the robot is going to do and why. Okay? Again, in critical scenarios, you need to, in order to have confidence and trust in what's going to happen, you want to understand why there is this particular plan for this particular robot. The second scenario is this. So, oil and gas, offshore drilling, there was a talk at last ICAPS, the Spark workshop from Derek Long, on how planning is used also for oil and gas, let's say, scenarios. And even here, given that the consequences of executing a plan in this domain can be dangerous but also very costing, to have confidence on what's going to happen, it's very important. And finally is this, which we just started. And the idea here is that there is a lot of work around using satellite images for many, many things. We are focusing on the maritime domain, so using satellite images for checking unusual situation, emergencies, illegal behaviors. And the problem they have is that they get many, many images from the satellites, but they don't know how to handle all this information. There is, for example, information overflow, meaning there is too much information. You don't know, not even know when to look at first. I don't know if you know, but in the cockpit, in the planes, the environment is dark, so that every time there is an emergency, there is a red light telling the pilot, look at this, right? Rather than getting lost within so many, lights. We try to do something similar in this scenario. So here, explainable planning and planning must be used for what is called situational awareness, meaning you want to use planning for prioritize the messages to be sent to the operator and also to suggest the operator what to do. Another reason for looking into explainable planning is this. So this GDPR, which is a new regulation, which is, creating a lot of issues, let's say, in Europe, but not only in Europe, right? Many people talk about privacy, and in fact, the primary focus of the GDPR is privacy, but there is also this article here this one, that somehow says that the user has the right to understand the logic behind the way data are used, right? Means that if you use any recommender system, for example, you might have the right to ask why Netflix suggested this movie rather than this one else. So there is the need also from a legal point of view about explanations. Now, you probably all know DARPA program and the Explainable AI program. Can I just ask if you don't know about Explainable AI program? So, it's not obvious to everyone. Good. So, this is a big program launched by DARPA a while ago, a couple of years ago now. And this is basically the objective of the program, to try to create AI systems able to explain themselves, to make clear to the user why they are doing something rather than something else. And the focus, as you can see here, is in machine learning when this program was launched. And this is the manifesto of the program. What they say is that at the moment, if you use a neural network for image recognition, you give this input, and the neural network just tells you this is a cat. Why? Well, we don't know. It's a cat. That's the answer from the neural network. What they would like to see instead, it's a neural network able to say, I can say that this is a cat because there are some features that I recognize that make me think that it's a cat. So to give this sort of explaining why the neural network in this case is saying that that's a cat. But that's a long, it's a very challenging and ambitious objectives. And just to clarify, everyone in front of AlphaGo talked about this move as a great success of AlphaGo, right? Meaning did something unexpected which made the AlphaGo win the game. To me, instead, that's the stronger limitation of AlphaGo, meaning there is something that you don't predict and you didn't expect. Now, if it's a game, it's fine, but it's a surgery, it's not so nice. So, as a matter of fact, you cannot give any guarantees about the future behavior of your neural network, which is something that instead planning can offer something different. But we'll go to that in a bit. Now, there are some successes already, of course, in the data-driven AI in terms of explainable AI. Trevor Darrell and his team, they're doing a nice bunch of work on trying to explain deep neural networks by GAN. Good results, although still preliminary, while Barry Smith and his team in Dublin, they're trying to explain recommendations. So the example I mentioned before, while the recommender systems give you some suggestion rather than some other suggestions. Now, as we all know, AI, though, is not only data-driven, but it's also model-based, right? And particularly, you need to use model-based AI, at least in the following cases, where when you don't have data to learn from, or you don't have time to learn, or your model evolves, changes so often and so quickly that you cannot repeat the training every time. Okay. Many people would say, well, actually, there is something in between, which is learned model-based AI, when you learn your model from data. But in this case, giving guarantees about safety and trust of your model and your solution is not so easy if you learn the model from data. But that's a different topic. Let's focus on XAI and XAI planning. Now, the reasons for, I mentioned this already. Anyway, there are need for trust, for interaction, and for transparency. These are the main reason for wanted AI to be explainable. That's important, transparency, because when things go wrong, you want to know who to fire, really. There are also legal responsibility and accountability issues. Planning is well placed to address these challenges because eventually planner can be trusted. It's easy to allow an interaction between the planners and the humans, the users. And also, planners are transparent, which does not mean that if you take the code of PopF, it's trivial, right? So it's not meaning it's simple, easy, but you can trace the behavior of each planner. You can always do that with our planners. The algorithms are, again, transparent. Okay, now there is a lot of related work in plan explanation. Over the last 20 years and more, plan explanation has always been a very important topic in the planning community. However, plan explanation focuses on helping you understand what the plan is saying. However, making sense of a plan is a different problem than explaining why there is this plan rather than some other plans. However, we can somehow leverage this previous work. Some more recent works instead, they focus more on adding transparency or explaining plans. Now, the problem is that nowadays planning has been used in many critical domains. I mentioned some of them, and plans are also more complex than before. Particularly also when you go to robotics, things get complicated. So explaining things becomes more important on one end, but also more challenging. Now, in last year, in a paper called Explainable Planning, we tried to write down a roadmap of questions that we think explainable planning should address. What I want to do now, in the next 20 minutes and then I'm done, is to, even less, is to give you an overview of this roadmap and then give you a brief summary of the ICAPS workshop on explainable planning that we had 2 weeks ago, just to give you an idea on where people are in the ICAPS community. So in case you want to follow up, you know where to start from. So first of all, what explainable planning is not, and is not explaining the obvious, right? So we know that many planners, as we have seen, select actions by, for example, minimizing the heuristics, right? Checking what state is closer to the goal. So if the question is, why did the planner do that? The answer cannot be because it got me closer to the goal, because this is the obvious, right? It's not an explanation, it's just telling what is obvious. Instead, we should try to uncover a piece of knowledge that the user believes should be available, right? Which is not obvious from the planner. Now, these are some of the things that should be explained. The first question are this one. So, why did you do that? So, this is the user asking the planner, which is actually a form of this second question. Why did you do that rather than something else that I would have done? Because planning is also more interesting where the planner suggests something different from what you would do. Otherwise, perhaps it's just common sense. Or a variant of this question is, why what you propose is more either efficient, safe, or cheap than something else that I would have done? That's very important, particularly in terms of efficiency. Users might expect some different plans to be more efficient than the one that the planner found. Why cannot you do that? So, in many scenarios, the user would expect some plan, but the planner say, no, that's not feasible. And then also, these are all questions when the user is confronted with the plan and needs to accept or reject the plan. But there are also some questions at execution time. For example, why do I need to replan at this point, or why do I not need to replan at this point? I'll go through this question very quickly. As I said, why planning is well placed to address the issues of explainability. First of all, because it's based on models, well-defined and well-understood models. Plus, the execution of plans provides you execution trace that you can analyze post-hoc. Plans causality is explainable, meaning that you can see the reason why there is one action before the other and what's the relationship between the two. And heuristics are recomputable, means that you can explore the behavior of heuristics even after you use them for the first time. Now, the first question, why do you do that rather than something else? And the idea here, is to use this kind of approach. So you have a plan, the user is questioning you about one action in the plan, so you can use the planner itself to provide what are called contrastive explanation. I'll show you with this graph. So suppose this is part of the plan. So you have actions here until to state S, then the planner suggests action A, and then the rest of the plan. But the user says, well, actually, I would expect action B instead of A, right? That's a question that the user can ask. So what you can do is to take the plan, to get to the point where you reach the state S, inject action B rather than A, and then ask the planner to replan from that, and see what happens if I accept the solution from the user. So one way to provide contrastive explanation is that, okay, let's assume you're right, let me take your action, and then let's see what would happen. Now, if we do this, if your planner is good enough, what the planner would do is just to undo the user action and go back to the initial plan. So if your plan is good, you should do this. So one thing you should do is you should disable this option and really explore, the alternative plans. Even if this is the scenario, meaning that by injecting the user action, you have some other actions and then you go back to initial plan, then you can do that is that you can measure and give an evaluation of the different plans and show the user that the original plans were actually more efficient, or anyway, no worse than the plan suggested by the user. That's an example of contrastive explanation. You can also find that you find a completely different plan, and again, you can evaluate both, or you can find that because of the user action, you can no longer find any plan. And these are examples that you can use to convince the user and give the user more confidence about your plan. Please.
For example, in the case of mediated systems, where you have the case of a very indicator and where you sometimes you cannot reproduce the exact state, even, you have a complete plan, you don't get the same state. So, is there a way to validate that?
Well, that's a good question. This setting is for setting where you have a deterministic model, right? And you can always reach this state S. How to handle the uncertain case is an option. I mean, it's an open question for sure, but the point here is that if you have the model that the planner uses, you can explore the alternative plans that the planner could produce. Okay? Any other questions? Okay, there is an illustrative example with PDDL so that you see how this can work in practice in PDDL. That's an example from the rover, the temporal version of the rover domain, where we have a couple of rovers, R0 and R1, and a number of waypoints, and the rovers must collect data and send data. So assume the user is confronted with this plan, and one question the user can ask is, why did you use rover 0 to take the rock sample at waypoint 0? Okay, so here we use rover 0, and the user asks, why are you using rover 0? Now, one answer could be, so that I can communicate data from rover 0 later, okay? But that's what we call a stupid question, right? Why? Because of course, if you use rover 0 to take the sample rock, you must use rover 0 to send the data there, right? The question is, why didn't you use rover 1 instead? So what can you do is basically, okay, that's the real question. So what can you do then is to basically remove the ground action instance for rover 0, meaning you prevent the planner to be able to use rover 0 for that particular action, and you replan and see what happens. And this is the new plan. And what you can show is that, okay, by using rover 1 now, the plan will have a duration of 10 units of time longer than the previous one. So that's an initial explanation. However, are we happy with this plan? That's a tricky question. Or in other words, suppose you are the user. Would you be happy with the answer, or would you keep challenging the planner? Look at the new plan. Anything unusual or strange? Correct. Who said that? Okay, that's a very good point. Exactly. Now, it's only using rover 1. So what's the follow-up question if you were the user of this planner? Why are you using only rover 1? Right. Okay. So this is a question that can be asked. So that's, sorry, this was the answer. So I would get a longer plan. So, but why does rover 1 do everything in this plan? So what you can do is that you can force the plan to contain at least one action that has rover 0 as one of the parameters, right? How you put that in the goal? I mean, there is a number of structured and formalized way on how to translate this question into ways you can update your model in order to constrain your planner to find alternative solutions. And that's the planner, the new plan. Okay, comments on this plan? Well, you are right and you are wrong. It's using both, right? Exactly. That's more precise, meaning that there is no useful way to use the rover. Okay? So in a sense, the planner is, obeying, right? He said, okay, I will use, but as you said, for a completely useless thing. There is then the follow-up question is, can you use rover 0 for something actually meaningful? And the idea then is that you constrain your planner to use rover 0 for an action whose effects contain something which is in the goal. Right? But I can show you, the answer is no plan can be found. So at the end of the day, you end up in having kind of evidence or justifications, if you want, that the initial decision was the good one of using rover 0. But again, the idea here is to show that exactly because you have a model, you can play with the model and check and explore the alternatives. This is something that cannot be done with the neural network, right? You can only leverage having models. And again, I'm stressing this, I'm very passionate about that because this is a strong point from planning that we should be very aware of. Okay. Just to point now at some I mean, there are open questions, but there are not so many solutions to explainable planning. Just touching on which techniques we could leverage in the planning community to address these questions. So, well, what you want to do is more efficient, safe, cheap, and something else. And the idea here is that different metrics can be used to evaluate the plan. So I mentioned VAL before. What is nice about VAL is that you can use different metrics, almost every metrics, for evaluating different plans. Okay, so when we are confronted with different plans, you can use different metrics to give evidence that some plan is more efficient in some other plans. Okay, then why cannot you do that I would have done? Now, there are two reasons why you cannot apply one action in a current state. One is that the current state does not satisfy the action precondition, and this is a trivial situation, right? So if the waypoint, if the rover is in waypoint 0 and the rock is not in waypoint 0, you cannot take the rock sample. But the other reason, which is more, let's say, tricky, is that using that action could prevent achieving the goal. And this is more tricky because it's not easy to demonstrate that one problem is unsolvable. So there are, though, a number of works around proving unsolvability, including including a planning competition. So all the techniques around unsolvability, proving unsolvability of problems, can be also used for explaining why something cannot be done. Okay, just to highlight this one thing, that human autonomy teaming or human AI interaction is the idea of users interacting with the planner, in this case, with AI. And the way the user can interact with the planner is either modifying or suggesting revision to the model, but also playing with the plan itself, so injecting action or removing actions. Also because another thing that I'm experiencing with my team is that when you work with people in real scenarios, you find two things that you don't find in other scenarios. The first one is that you are proposing your planners to people who have 20 or 30-year experience with satellites or other scenarios, and you don't want to say, I will replace you. You want to use their expertise. And they also have the right to say, yes, I want to, to be able to help somehow and to use my expertise too. The second thing that you find is that you always have humans who are in charge of accepting or rejecting plans. And before accepting or rejecting plans, they want to have guarantees about what's going to happen. Explainable planning at execution time. Now, why do I need to replan? Well, very briefly, the problem is that in many occasions you have to replan, and the later you discover that, the sooner you discover you need to replan, the better, because you avoid situation when you can no longer recover from where you are. One approach is, we propose to use filter violation in ROS plan, and there are, I'll go very quickly here, and there are a number of experiments we did in underwater robotics. The idea is that while you are executing the plan, you can observe a number of safety properties that you put in a knowledge base that you know must be true through all the plan for the plan to be valid, so that as soon as you spot that some of them are no longer valid, you can stop and say, okay, we need to replan. But this is an open challenge. Again, I'm not saying it's solved. Why do I not need to replan at this point? This is even more interesting to me. Now, given that, again, in practical situations, the state, the real state, will always be different from the predicted state, or almost always. Now, the point is that we don't want to be naive and replan at every single discrepancy we find. Otherwise, we end up in a continuous replanning cycle. So we want to understand whether the changes in the state are still good for your plan to be valid. Sort of tolerance. There are a number of promising directions, in my opinion, on this. Something I'm also personally exploring, again, was rejected last ICAPS, but the idea is to use SMT to dynamic control, for the dynamic controllability of plants, meaning that you can create around the plants a sort of robustness envelope that basically tells you, for example, how long your action can be delayed. Okay, so you can say the expected action was 5 minutes, now I'm at 5.20 seconds, and the level of energy is less than anticipated. Am I still okay or not? This can be done. Related workshops, just to give you an idea that the community around this is quite, live and active. There were 2 workshops at EJKI on explainable AI, where the focus was on everything but machine learning, right? So the idea of looking at explainable AI from different perspective. This mainly thanks to the effort of David Hea. I need to acknowledge his effort on this. And last June, we organized this first workshop on explainable planning at ICAPS. A brief overview, 5 minutes, and then I finished, on what the community is doing since we started talking about explainable planning. So this work from our friends in Australia focus on action selection for transparent planning. Now, transparent planning, in a nutshell, is the situation when you want someone who is observing a plan to know what the goals are. So to be transparent in terms of the goals your agent or your robot is achieving. Now, either you communicate this goal explicitly, say that's my goal, or you do it implicitly through, for example, the action that you do. So, for example, the idea is that here is easier to get, to think at where R is going to aiming, basically. So they made there is a nice paper where they propose a formal framework based on probabilistic planning recognition, and they, talk about how actions can be used to explain the goal they are achieving. Now, this work from Felix Robert and Bernard Bell is, they did a nice thing. So they took the question that we put in our explainable planning paper, but they added an additional layer, which I think is very, very interesting and remarkable. So why what you are suggesting is more efficient, safe, cheap, or morally better. So to introduce the moral layer on explaining why something is better or worse than something else. What they did is they provided this taxonomy, let's say, of criteria or values to be used for evaluating whether a plan or an action is more morally good than something else. And these are the questions they are now trying to to answer. First, can we create morally competent planners? And the answer is no, not yet. Okay. What they do so far is to evaluate how morally competent a plan is, rather than creating the planners. That's very interesting. I mean, it's quite easy to say whether one action is morally good or not. But how do these translate into a general plan? Because one action might look morally good, but the effect in the whole plan might end up in something which is not morally good. So I think these are very interesting questions. They are trying to formalize. So this is from a company. Christina was at the DAG2 workshop I mentioned before. At the company Satire, they are trying to explaining AI, which they do using mathematical optimization. Okay, I found this very interesting because, again, it's yet another area of explainable AI. And what they do is something like, so these were the motivation from their slides, and what they do is that they, for example, do sensitive analysis to provide the following answers. So no solution exists because the set of constraints is, the problem is over-constrained, or an optimal solution exists for this objective and all the constraints are satisfied. However, as Christina, who gave the talk, acknowledged, these are not explanations yet, because the real explanation would be why there is no solution, why the problem is over-constrained. and I mean, they don't have a solution yet, but it's interesting to me to see that people are at least are raising important and interesting questions. Then there is a nice line of work from Subarao Kambampati team, and they are focusing on all cases where I have a model of the world, but the robot has got a different model of the world. And the problem of explanation there becomes how to reconcile or how to reduce the differences between my model and the robot model, so that we can come up with an understanding on why the robot plan is different from what I would expect. And finally, these work from many people actually, but the idea is they created this framework for visualizing a plan and adding in this visualization some explanations. So for example, links between the current action and the previous action. What is also interesting is the work that has been done in planning on top K plan. So instead of generating only one plan, I generated the first K good plans. And that's also, I think, very relevant to explainable planning, because it's one way to help the user to understand, for example, which flexibility we have, which range of efficiency we can achieve. This is work in collaboration with the Navarre Research Lab. They work on goal reasoning agent. And what we consider here is the problem of agents rebelling, right? And that's an example where there is an agent working with a human to achieving some task, but the robot rebels, so it disobeys, in this case because it's observing something which is not known to the user that would put her in danger. There are many reasons why rebellion is good, right? For example, because the robot has got more information than the user, and he discovers that there is something that would be dangerous. But however, when you have an agent rebelling, for sure this agent needs to explain you why it's rebelling, otherwise you just switch it down, right? So it's in the context of agents, and these are the reasons why it's good, could be good for an agent to rebel. And again, another work led by David Ea and his team is about explaining the behavior that changes because of changes in the goals, okay? So you have a current plan, but your plan must change because there are changes in the goal. So their goal changes. So you want to provide an explanation that allows you to understand why the new goals require the new action. Again, they provided a taxonomy and a set of dimensions from which you should explore the explainability problem. So there is a lot of future works in explainable planning. That's absolutely a non-exhaustive list, but the first 2 points, I think the main important ones is, first, how to say whether an explanation is good, because an explanation could be good according to myself, my knowledge, my preferences, but perhaps for someone with different knowledge or different background, it's completely nonsense. So what is a good explanation? It's an open question. And more importantly, we need to give evidence about the benefits of explanation. So this is a domain where it's not, you cannot just run the IPC benchmarks, right? You need to be able to do user studies, for example. And this is something perhaps a bit new to the part of the planning community at least. How to give evidence of your experiments through, for example, user studies. And for this, I think that the synergy between, as I say here, between planning and other areas like cognitive science or social science is really important to be able to join forces. Temporal explanation, why goal A is achieved before goal B. As according to the question before, what if you have probabilities, uncertainties? Okay, these are all open questions. So more questions than answers. And also, more importantly, XIP is not just, planning is not just PDDL planning, of course. What I show here are some examples based on PDDL, but we should go much beyond PDDL and also address planning in a much broader sense. Finally, so this is fruit of a synergy between explainable AI and security. Luca Vigano is a colleague of mine who is an expert in security, cyber security, and we thought about explainable security, meaning that if you want to deal with security of your robots or your systems, you want to be able to explain while your system is safe and secure. You cannot just say, yes, this is secure. You want to give evidence, as we do for AI, on why the security system is, accurate and reliable. And the most important slides is that I really need to thank my teammates. This is how we have our meetings usually, with a beer and was from ICAPS. Thank you very much. Okay, if you have questions now or offline, as you prefer, I'll be around. I should remove the picture, it's distracting, right? So. Yeah.
So weren't you afraid when you were in this ether without driver receiver? Weren't you afraid?
No, only for the reasons that there were 2 humans there. That's exactly the point. It's the only guarantees at the moment. Please.
You started looking at working with people in social sciences and political sciences to work on your project. Do you have any projects that you're working on?
So, yes, in terms that I have colleagues who are interested in this. And we are looking at how to work on this. I have to say that there is a very nice work from Tim Miller. He wrote a paper called Explainable AI Insights from Social Science, where the idea is that he's looking at how social science can help AI, explainable AI. And the main point is that if we want AI systems to interact with humans, we should look at the social science where they are looking at these human interactions to learn from them and to help each other. So the answer is yes, there are people and we are trying to do it. Okay. Yes, please.
How do you evaluate these methods, like the verification methods that you said direct the robot take that path, and you said that the robot took that path to know the other path was no. So how do you evaluate the correctness of that quantification?
So I guess there are two questions here. How to evaluate the plans and how to evaluate the explanations. Okay, how to evaluate the explanation? That's a very good question. And as I said, there is not a clear answer on whether the explanation is effective or not. For sure, it's not that there will be, in my opinion at least, there will never be a unique format. For sure, there will be criteria that we need to satisfy in our explanation, but the format will definitely depend on who you are talking to. So you are talking to domain experts or non-domain experts. Second, depends on how complex is your plan, because if your plan is, 10 actions, that's okay. But if your plan is 2,000 actions, as we do have, right? Perhaps you need the hierarchical representation of plans. You cannot show the user 2,000 actions, right? You need to have a kind of hierarchy, for example. So I think it really depends on the users, but as I said, we need to ask for help to people who know more than us in this domain. Social science, for example, and do user studies. Emre?
Has anyone in the community considered explaining plans generated by stochastic planners? So you can definitely explain based on causal links, but when it comes to probability, how do you...
No, that's a good question. I don't know. I mean, again, there is... so your question was, is there anyone who looked at this? No, the answer is no. There is well, what I can say is there is a very promising proposal that Jörg and I got accepted, so we'll be working on these things. But of course, this is a great question, and I hope that the goal of this part of the talk was to raise awareness and interest around open questions rather than answers. There are a few answers which are promising, but many questions, including probabilities. No solution yet. Please.
I was just thinking that these kind of questions, why did you do that instead of this? So
Suggested actions could be better.
Now, thank you very much for your question. This is a really great question. So, okay, let me phrase this way. If you can find optimal plans, there is not so much need for explanation. In the sense that if I can prove that the plan is optimal, I mean, what are we? No, you cannot disagree if I can prove it. However, optimal plans are, in real scenarios, to me, are very rare, to say the least, right? So that's why you need to provide contrastive explanation. Means allowing the user, as you said, playing with the planner. And you are absolutely right that one outcome of having the contrastive explanation, let me go there, one outcome could be that the alternative is actually better than what the planner found. I absolutely agree. So it could be the case that these end up in being cheaper, for example. So I absolutely agree. But just to clarify, you need these exactly because you cannot provide optimal plans by construction. Otherwise, that will never occur, right?
That would still be a reason why I want to do that, because you build a model of that problem. So now it would expose like the weaknesses of it. Oh, you didn't model this, that's why.
Fair enough. Absolutely. Again, yes, that's sure. But again, okay, that's a very good point. Thanks for commenting this, because even the model, I didn't mention this, but even the model is something that you can show the user. So you can tell the user, look, I modeled this, but I didn't model this. Right? Can you do something similar with a neural net, for example? Again, just to leverage the fact that planning has got some ingredients that make planning a good potential. Thanks for the comment.
How do you maintain and update the notion of trust?
How do update and maintain?
Yeah, the notion of trust over time. How do you build trust with somebody? I mean, the whole goal of this
Yeah, that's...
AI is to
Yeah.
how do I measure trust from that? Have I done enough to prove that?
That's a great question. I can only say that if you're using a planner, the first time I will provide you one kind of explanation. After 50 times, I need to provide something different, something else. You are absolutely right. Trust, also your confidence on the planner, your knowledge of the planning system evolves over time. So that's definitely nothing static. I don't know the answer, but for sure you are right that it needs to be dynamic and change over time. True. Please. Is the goal to improve? Yes. So you're talking about the model of the trust for humans. No, that's a very good comment. I guess on one hand it relates to studying cognitive science and social science, because I have no experience, so I need to ask for help, right? I guess the contrastive explanation is the basic level you can use for any kind of user, right? Showing A and B. And do you want to say something more? Please. Good point. So she's saying you should relate trust to transparency and risk, and I agree. That's a good point. Yeah. I mean, I completely agree also on this. And I guess what I mentioned about situational awareness is about this as well, right? So you don't want the user overtrust the system. That's why you want to somehow not force them, but to invite them to interact with the planner. But unless you create a system that makes this interaction easy, otherwise it becomes difficult for the user to interact. They either trust or they ignore, right? But you are definitely right. Okay.
Thank you all. So we have a half an hour break. So let's meet at 4:30 in the lab, the same room as yesterday, room 124 for the PDDL lab.